dear friends. My name is Gleb Burdonov, this is Anton Poltoradnev, and this is Roman Davidov. We are Rocket Lab. This is a student bureau which creates experimental rockets. And today we are going to talk with you about many things. We'll start with the history of space exploration. We will tell you about some basic laws of physics and of rocket science, of course. And towards the end, we will tell you about one of our projects, a two-stage experimental rocket called TSR, two-stage rocket 2.0. So let's begin. Let's open slide. Our number one. Yes, let's open our slide. You can turn on your cameras. We can see you. That will be better for us to understand your interests. Сейчас мы презентацию включим. Да. Ага. Выключил или не выключил? Микрофон выключил. Да, мы забыли презентацию совсем. Включил, выключил. So guys, we have some technical problems here. Tell us something about yourself. Which university are you studying? Do you have any plans to go to Russia near after COVID-19 pandemic? And do you have a really big interest? Are you really interested in rocket science? Because it's a very, it's a very big. It's a very big. Tell us about yourself, please. Are we trying to find a presentation for you? Why do you choose Samara University Summer School to be with us today? Maybe it's something like that. Now we're trying to find our presentation because we have some technical problems. And as I said previously, today we're going to speak with you about history of space exploration. I think that's most interesting part for you, because after that we have some words about basic laws of rocket equations, basic laws of equations, basic rocket equations, basic laws of physics, and it's just so basic. So you know, first, second, and third law of Newton's law about rocket science. I think you also know the famous Tsiolkovsky equation. That is a pretty common thing in our field of study, the Tsiolkovsky rocket equation. And we also tell you something about our own project called Two-Stage Rocket 2.0. That's a really, really big project. It was created for competition in France called Space 2020. And we take a special prize for it because it was two-stage rocket. It's successfully, our stages can be separate each other. It's successfully separated in our competition. So that was pretty big work for us. And of course, we'll try to tell you about it because it is really interesting for our students. Oh yeah, I can see all of you. That is really great. Hello, everybody. We can see you, we cannot hear you, but that's okay. So we are already fine our presentation. We're ready to start, I think. Now I just download it. So we will start with Konstantin Tsiolkovsky, of course, because it's it's a main thing in Russia's rocket science. It's Konstantin Tsiolkovsky's name, and of course Sergei Korolev, of course. Yes, that's a pretty two biggest names in rocket history, two biggest names in Russia's history of rocket science, rocket engineering. So now we have some antivirus check here on our computer to open our presentation. Please open our presentation. Okay, just open it from our USB dock. So yeah, we are ready to start. Please, can you open our presentation? Pardon. Открой Zoom. Правая кнопка. Yes. So yeah, we're ready to show you our PowerPoint and our presentation. So now you can see it. Can you open the full window, please? So yeah, can you tell something? You can hear us, you can see us, you can see the presentation. That's okay. You can just, oh, thank you. So let's finally begin. So let's move to the slides. Yeah, how did it all start? So in the beginning of 20th century, the Russian school teacher Konstantin Tsiolkovsky proposed the idea of using rockets as a vehicle for space exploration. He was the first man who wrote about rockets with several stages, acknowledged that the main bottlenecks of achieving such a feat would require significant developments in the range of rockets. Tsiolkovsky understood that the speed and range of rockets was limited by the exhaust velocity of propellant gases. In 1903, so it's 1903, that's a really, really long time ago, research into interplanetary space by means of rocket power, Tsiolkovsky suggested the use of liquid propellants and formalized the rocket equation, relating the rocket engine exhaust velocity to the change in velocity of the rocket itself. Now that's equation, of course, known as a Tsiolkovsky rocket equation, in his own, of course. So Tsiolkovsky also advocated of the development of orbital space stations, solar energy, and the localization of the solar system. One of his quotes is particularly precise in considering Elon Musk's plans to colonize Mars. The Earth is the cradle of humanity, but one cannot live in a cradle forever. In a letter written by Tsiolkovsky in 1911. So Tsiolkovsky knows Elon Musk's thoughts in 1911. That's pretty great. So his works, Tsiolkovsky's works, later inspiring leaders, Soviet rockets engineers such as Sergei Korolev and Valentin Glishko, and contributed to the success of the Soviet space program. So now let's move to our, some modern history about Tsiolkovsky. From weapons to space exploration. After World War II, the United States and the Soviet Union began heavily funding research into ICBMs, it's intercontinental ballistic missiles, partly because these had the potential to carry nuclear warheads over long distances, and partly due to the allure of being the first travel to space. The key figure of USA future space program was Werner von Braun. It was a captured German scientist. His rocket V2, or V2 in Russian, was developed during the Second World War in Germany as a vengeance weapon, assigned to attack Allied cities, London, as retaliation for the Allied bombings against German cities. In 1969, his rocket called Saturn V, you all know Saturn V and Apollo 11 mission, I think, will launch a man to the moon. But in the first part of space race between USA and USSR, the initiative was held by Sergei Korolev, it was previously mentioned with us, by Sergei Korolev, Soviet one-man version of NASA. Under his leadership, the V2 was used as the basis for the first rocket ICBM, for the first Soviet ICBM rocket, called R7. The R7 was further development into Vostok rocket, which launched the first satellite, Sputnik 1, into orbit on October 4th, 1957. So the orbit, October 4th, it's a date that in the world, this date is famous for start of space exploration era for the humanity. So the launch of Sputnik 1 started the space race, and the whole era of space exploration began in the history of mankind. Now let's watch a US TV program from 1955, where Werner von Braun, captured German scientist, explains the possibility of traveling in space. Anton, can you open our first video, please? Our first video, not our second or first slide of presentation. So yeah, this is basics of rocket history. So that's some words about Werner von Braun. He will tell you some interesting things about rocket equations and about rocket laws. And after that, we'll go further into a space race. That's a pretty interesting thing. Anton, you need to open your Google Chrome, please. It's left here. Yeah, thank you. Number 1. Yes, that is it. So now let's watch it. Can you see the volume of our video? I will try to understand that. Just try to watch the video, and I will. Can you see the volume of our video? We have some technical issues here.
We cannot see the video. We only see the PowerPoint, the slide.
Okay, we'll only see a slide. Yeah. Okay, now we'll demonstrate your video. Please demonstrate how Google Chrome, Google Chrome. Okay. So yeah, now you can see it just right now. You can see it. And please, Anton.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Werner von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would do the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that men can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model I designed for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel, and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the 4th stage. This would also give the crew more and more training. Following that, the 3rd and 2nd stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights would be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge 1st stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space. Let's look ahead a few years and see how this might be accomplished.
Yeah, now you can hear us. That was a pretty amazing video because it was from 1955, and of course, Werner von Braun had a pretty big German accent, so it's hard to understand him when you knew English as your second language. So the space race, as we already mentioned, began in 1957, I'm sorry, when Soviet Union launched the Vostok rocket, the first ever satellite on board, Sputnik 1. That was a real revolution. Sputnik 1 was the first man-made object in space. Let's see some historical footage of this event with comments from amazing YouTuber in space. It's called Curious Droid channel. And can we launch our second video, Anton? So Anton is our technical advisor here. After me, he will tell you something.
That simple beep, beep, beep was the sound that started the space race. It was heard for the first time 60 years ago, when on October 4th, 1957, the Soviet Union launched Sputnik 1 into low Earth orbit. It was only a metal ball 22 inches or about 56 centimeters in diameter, with 4 antennae sticking out of it, but it had an impact far greater than its size. In fact, it changed the course of human history. The idea of a satellite was first raised in an engineering memo written by Mikhail Tikhonravov in 1954, whilst his former boss, the Soviet space program's chief, Sergei Korolev, worked on what would become the world's first ICBM, or the R-7. Tikhonravov thought that if a missile could carry a nuclear warhead through space on its journey from one side of a planet to the other, it could launch a satellite into orbit too. Korolev immediately saw the potential and pitched the idea to the Minister of Defence, Dmitry Ustinov, and on January 30th, 1956, a governmental resolution was issued calling for the production of an unorientated satellite known as Object D, weighing in between 1,000 and 1,400 kilograms and containing scientific research equipment. However, it wasn't just the Soviets that were looking to place a satellite into space. In the US in 1955, American President Dwight D. Eisenhower pledged that his country would launch a satellite during the International Geophysical Year, which was to run from July 1957 to December 58. Shortly after the start of the Soviet project, test firings of the R-7 rocket showed that it was not generating as much thrust as was first thought, and whilst this was okay for a warhead delivery, it might not be enough to launch the 1,000 kilogram plus Object D into orbit. In order to launch quickly, they had no option but to build a much cut down version called the Prostichi Sputnik, or simple satellite, the simple metal sphere that we know of today, weighing in at just 83 kilos. Inside the spherical heat shield was a sphere pressurized with nitrogen, containing 2 transmitters, 3 silver zinc batteries and a ventilation fan. Sputnik Sputnik was launched on October 4th, 1957 from the Toratam rocket range, now known as the Baikonur Cosmodrome in the Kazakh Republic. It was delivered into an elliptical orbit with a maximum height of 900 kilometers above the Earth and began orbiting every 96.2 minutes, travelling at a speed of 29,000 kilometers an hour and transmitting on two radio frequencies, 20.005 MHz and 40.002 MHz. Boris Chertok, academic and one of the senior designers of the later Yuri Gagarin flight, stated that there was a common misconception that the shiny sphere of Sputnik was just about visible to the naked eye and was easily seen through binoculars. But in fact, what people were seeing was the second stage of the R-7 rocket, which was in the same orbit. Sputnik itself was just too small to be seen. In fact, it had already flown over the United States twice undetected before the Soviet news agency TASS confirmed its existence to the world. Everyone with the right radio equipment could hear Sputnik's beeps, and although that's all the satellite actually did, scientists were able to measure the distortion of the signal, allowing them to make the first accurate measurements of the upper atmosphere's density and gather early information about the Earth's ionosphere. But the satellite was much more than a bleeping sphere. The impact was instant and global, an event known as the Sputnik moment.
So that was pretty interesting. That curious droid is always interesting. So let's resume our history of space exploration. So, no, previous slide, please. Sputnik was a big step in space exploration history, but there was a next milestone, launch the first human to space. And this achievement once again belonged to Soviets. On April 12, 1961, the cosmonaut Yuri Gagarin became the first human to travel into space, and as a result became an international celebrity. That was a really, not revolution, that was boom in space exploration. Over a period of just under 2 hours, Gagarin orbited the Earth inside a Vostok 1 or Vostok 1 in Russian space capsule at around 300 kilometers altitude, and after re-entry into the atmosphere, ejected at an altitude of 6 kilometers and parachuted to the ground. At this point, Gagarin became the most famous Soviet on the planet, traveling around the world as a beacon of Soviet success and superiority over the West. So that was pretty interesting. Can I open a video for? Let's see how it was. That was a real, not just a revolution, that was a real boom because, you know, first Sputnik, first satellite, that's a really great achievement. But first man in space who traveled.
It's April the 12th, 1961.
Kilometers, that was really, really great. So let's watch another video about it.
It's April the 12th, 1961, and the Vostok 1 capsule has started its re-entry to Earth's atmosphere. However, all is not well. The service module, which should have separated from the re-entry capsule, is still attached. High above Egypt, the little spacecraft is being thrown into wild gyrations as the two parts heat up in the upper atmosphere. Inside the capsule, the first man in space, Yuri Gagarin, assesses the situation as he experiences up to 10 times the force of gravity. In his own words, there was a moment, about 2 to 3 seconds, when the data on the control gauges started looking blurry. It was starting turning grey in my eyes. Yuri Gagarin was born on March the 9th, 1934 in Klushino, a small village just over 100 miles west of Moscow. His family were peasants before the revolution, and when Yuri was born were working on a collective farm. During the war, Klushino was occupied by the Germans. The Gagarin residence was commandeered by a German officer, and the Gagarins lived in a 9 square meter mud hut in the land behind the house. The Germans sent 2 of Yuri's older brothers to work as slave labor in Poland. After the war, the family moved to Gzhatsk, and age 16, Yuri went to work as an apprentice in a steel plant. During this time, he took evening classes and after graduation moved to Saratov, where he studied tractors at the Saratov Industrial Technical School. He volunteered at the local flying club, flying on weekends as an air cadet. To make ends meet, he also worked as a dock laborer on the Volga River. In 1955, at the age of 21, he was admitted to Air Force Pilot School in Orenburg, and shortly after started training on the MiG-15. At 5 feet 2 inches, or 157 centimeters, Gagarin wasn't tall by today's standards. He struggled landing the 2-seater trainer and was almost dismissed from pilot training. He was given one last chance to successfully land the MiG-15. Yuri's instructor gave him a cushion to sit on to improve his view, and Yuri landed the aircraft without any issue. In 1957, Yuri became a lieutenant in the Soviet Air Force, and towards the end of 1959, at the age of 25, he volunteered for the Soviet space program. The selection program was rigorous. Pilots had to be between the ages of 25 to 30, weigh less than 72 kilograms or 159 pounds, and be below 5 feet 7 inches tall. 154 pilots were shortlisted and went through the intense psychological and physical tests. Finally, just 20 were approved. The men trained together and Gagarin was hugely popular. When the trainees were asked to vote who should be the first pilot to go into space, all but 3 voted for Yuri. The State Commission meeting on April the 8th, 1961, just 4 days before the flight, nominated that Yuri Gagarin would be the primary pilot, and Yuri's friend and colleague, German Titov, should be his backup. On the day of the launch in the bus on the way to the launch pad, Gagarin needed to pee. He asked the bus driver to stop and christened the back right-hand tire of the bus. This tradition still continues today, with all pilots taking off from Baikonur. The women cosmonauts prepare a cup so they too can splash the rear wheel. Gagarin entered the Vostok 1 at 0410 UTC and was strapped in. Launch was 2 hours away. Gagarin talked to Capcom and to Korolev. Korolev was a genius behind the Soviet space program and was so nervous he had to be given a pill to calm him. At this time, 50% of Soviet launches were unsuccessful, and everyone was aware of the odds. Unbelievably, during this time, Yuri asked for some music to be played and was described as calm. Half an hour prior to launch, his pulse was just 64 beats per minute. 3 press releases were already prepared, 2 for failure and 1 for success. At 0607 AM UTC, the engines fired and the launch began. Gagarin famously said, "Поехали," or "Let's go," followed by "Goodbye until we meet soon, dear friends," and Yuri Gagarin became the first man in space. Gagarin had no control of the spacecraft. The Soviet scientists were unsure what the effects of space would be, so to play it safe, they put a series of codes into a sealed envelope that Gagarin would open under exceptional circumstances, so that he could initiate the landing procedure himself. 11 minutes after liftoff, as the Vostok 1 capsule passed over the Soviet Union, Gagarin reported, "The craft is operating normally. I can see the Earth in the viewport. Everything is proceeding as planned." No one knows exactly what went through his mind at this time. He had time to eat and drink during his 108-minute orbit of the Earth. As a consummate professional, he was surely focused on his mission. However, the incredible achievement of getting a man into space just 16 years after the USSR was devastated by war could not have been lost on him. 53 minutes into the flight at 7 AM UTC, as Vostok 1 passed over the Strait of Magellan at the tip of South America, Radio Moscow announced the news that the Soviet Union had put a man into space. News that was to shake the world. The flight had been designed so that if retrofire was unsuccessful, Yuri would fall to Earth naturally after 10 days. The orbit was higher than planned though, and so natural orbit would have been 20 days, far longer than Yuri's supplies would last. Fortunately, retrofire occurred successfully about 1 hour into the flight and started to bring Yuri home. It was a very bumpy ride due to the faulty separation of service module and capsule. Gagarin wrote, "The spacecraft started spinning around its axis at very high speed. One moment I see Africa, another moment the horizon, another the sky. I barely had time to shade myself from the sun, so the light did not blind my eyes. But I did not close the blinds. I wanted to find out myself what was going on." Finally, over the Mediterranean Sea, the modules separated. There is still debate as to why this happened. Some have speculated that cables burned through in re-entry, separating the modules. Some that temperature sensors triggered separation. However, the separation did occur, and the Sharik re-entry capsule successfully entered the atmosphere. The bright glow of re-entry was visible behind the window shields. The thermal protection crackled, and an alarming smell of burning entered the capsule. At a height of 7 kilometers, Gagarin jettisoned the hatch and he ejected from the capsule, still strapped into his ejection seat. Gagarin landed separate to his capsule, a fact the Soviets lied about until 1971. The rules for the record book set by the FIA in 1961 stated that the pilot had to land with the spacecraft to be considered for the record, a rule that was later changed. Gagarin landed on a farm 500 miles south of Moscow by parachute in his bright orange spacesuit, near a farmer and her daughter. They were scared and started to back off in fear. Gagarin called out, "I am a Soviet citizen like you, who has descended from space, and I must find a telephone to call Moscow." Gagarin was awarded the Hero of the Soviet Union, and in Russia he was loved by the people, who called him Yura, which is the friendly form of Yuri. The world embraced the brave young cosmonaut and his winning smile as he went on tour visiting 30 countries around the globe, although JFK barred him from entering the US. Gagarin restarted pilot training, but the authorities were reluctant to have him fly again. To risk losing him would have been a disaster. He was backup for his friend, Vladimir Komarov, on the Soyuz 1 flight. Soyuz 1 was rushed due to political pressures, and Gagarin was unhappy with the safety of the craft. When Soyuz 1 crashed after its parachute failed to open, Gagarin was banned from any further space flights. The impact of Gagarin's achievement spurred the United States into action and pushed the moon landings forward, with JFK announcing in 1962, "We choose to go to the moon." On the 27th of March 1968, Yuri was on a training flight in a MiG-15 UTI. There are a number of theories as to what happened, including bird strike and a near miss with another plane, but it seems the aircraft entered into a spin that couldn't be recovered. The ashes of Gagarin and his flight instructor, who was also on the plane, are in the walls of the Kremlin. The Apollo astronauts Neil Armstrong and Buzz Aldrin left a memorial to Gagarin and Komarov on the moon. Yuri wrote a note to his wife prior to his spaceflight in the event of an accident. She was given the note 7 years later, after his plane crash. It talks of his hopes for his daughters and his wife and finishes, "Goodbye, my dears. I embrace you all tight and kiss you. Your dad and Yura."
So that was pretty bad at the end, but that's okay. That's okay. That is a Soviet Union rocket space history. That's the great. We of course pledge a great honor to the Yuri Gagarin and of course Vladimir Komarov. So after launch of the first human in space, Soviet Union was unstoppable. First spacewalk, first automatic docking in space, first ever photographs of the lunar far side. United States was second again and again. But there was a new milestone, moon landing. In 1962, as already mentioned in the video, John Kennedy, current US president, delivered a "We choose to go to the moon" speech. In his speech, Kennedy characterized space as a new frontier, invoking the pioneer spirit that dominated American folklore. He infused the speech with a sense of urgency and destiny, and emphasized the freedom enjoyed by Americans to choose their destiny rather than have it chosen for them. Although he called for competition with the Soviet Union, Kennedy also proposed making the moon landing a joint project. Now you can see when we open that "We choose to go to the moon" video, that is really the great speech. I think that is the greatest speech in US history and US president history, because for me, it's a really dazzling thing. So when I see Kennedy, when I hear Kennedy, that's really great. So let's watch it and just please listen, John Kennedy. It was a great man.
William Bradford, speaking in 1630 of the founding of the Plymouth Bay Colony, said that all great and honorable actions are accompanied with great difficulty, and both must be enterprised and overcome with answerable courage. If this capsule history of our progress teaches us anything, it is that man in his quest for knowledge and progress is determined and cannot be deterred. The exploration of space will go ahead, whether we join in it or not. We mean to be a part of it. We mean to lead it. For the eyes of the world now look into space, to the moon, and to the planets beyond. Our leadership in science and industry, our hopes for peace and security, our obligations to ourselves as well as others, all require us to make this effort, to solve these mysteries, to solve them for the good of all men. There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to us all. its conquest deserves the best of all mankind. We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
So yeah, that was pretty epic. And you know that Apollo program, as a result of that speech, NASA started an Apollo program. After 4 flights, the famous Apollo 11 mission had started. It was a space flight that first landed humans on the moon, as you already know. Commander Neil Armstrong and lunar model pilot Buzz Aldrin formed the American crew that landed the Apollo lunar model Eagle, called Eagle, on July 20, 1969. Armstrong became the first person to step onto the lunar surface 6 hours and 39 minutes later on July 21. Aldrin joined him 90 minutes later. It was a really great success. US returned their glory and overtook USSR. Now we can also have a video about the Apollo 11 program. It's about 5 minutes. And after that, we'll tell you something about Apollo Soyuz, the greatest corporation in space history. So let's watch something about the moon from Vox. That is a really great resource. Can you turn my mic off?
You're looking at one of the most incredible moments in human history. That's Neil Armstrong and Buzz Aldrin walking on the moon. Okay, maybe you've seen this clip before, but think about that for a second. They're on the moon, a celestial object nearly 240,000 miles into outer space. That distance is like flying all the way around the Earth 9.5 times. Millions of people around the world watched on July 16, 1969, as Apollo 11, carrying astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins, launched from Cape Kennedy, Florida, and disappeared into the sky. It was the climax of years of preparation and research, and the pinnacle moment of the so-called space race between the United States and Soviet Union, a years-long rivalry to compete for dominance in space exploration. For the 8 days following the launch, the world awaited the return of the would-be heroes. So what actually happened between here and here? So let's start with the components of the ship that were discarded one by one until this became this. Here's the rocket that sent the astronauts into space, the Saturn V. The 3 stages of the Saturn V each played a different role in launching Apollo on a path to the moon. We'll get to that later. On top of the rocket is the actual Apollo spacecraft. It's made up of 3 parts too. There's the lunar module, the component that would eventually land on the lunar surface, the service module, which had propulsion systems for course corrections and entering and escaping orbit, and the command module, where our 3 heroes were for most of the mission. And last but not least, this is the launch escape system, which was designed to pull the command module away from the rocket if something went wrong during launch. Together, all these pieces made up the Saturn V rocket and Apollo 11 spacecraft. But it's the way they came apart that made the moon landing happen. The Saturn V's first stage launched Apollo, carrying the spacecraft 42 miles above the Earth and reaching a speed of about 6,000 miles per hour. The first stage then detached, and once the Saturn V's second stage kicked in, the now needless launch escape system jettisoned too. The second stage propelled the spacecraft even farther and faster into space, and after it detached, the third stage of the rocket fired briefly to knock Apollo into a parking orbit, 103 miles above the Earth's surface. Here, final checks were made, and the Saturn V fired again to set Apollo on course to the moon, in a move called the translunar injection. Once the spacecraft propelled away from Earth, the Saturn V's job was done. Now, the astronauts needed to pull off a mid-flight maneuver to reconfigure the ship so the crew could access the lunar module, which had been stored in a protective compartment during launch. To do this, the command service module detached and flipped 180 degrees, docking with the lunar module and extracting it. In the process, they ditched the third, now useless stage of the Saturn rocket. This whole high-stakes launch process only took about 3.5 hours, and this, the completed Apollo spacecraft, was the end result. For the next 3 days, Apollo coasted through space, until it finally reached its target and was pulled into orbit by the moon's gravity. This is where the crew split up. Armstrong and Aldrin transferred to the lunar module, named Eagle, and slowly descended toward the surface, while Collins continued to circle the moon in the command module, called Columbia. Now, here comes another tricky part, landing on the moon. To make this historic moment happen, Eagle turned and used its engine to slow its momentum and ultimately touch down on the lunar surface.
The Eagle has landed.
The moonwalk was broadcast live on television, immortalizing Neil Armstrong's words here.
It's one small step for man, one giant leap for mankind.
I think that was Neil's quote. I didn't understand it.
No, one small step for man, but I didn't get the second phrase.
After about 21.5 hours on the moon, Eagle performed the first launch from a celestial body that wasn't Earth, leaving its landing gear behind and timing its ascent with Columbia's path in lunar orbit to rejoin the spacecraft. Once Armstrong and Aldrin transferred back into the command module, the lunar module was no longer needed. Just like before, Apollo needed to break out of orbit. This maneuver was called the trans-Earth injection and began the 2.5-day journey home. Upon approaching its entry point into Earth's atmosphere and no longer needing its propulsion engines, Apollo jettisoned the service module and prepared for re-entry, protected by the now exposed heat shield on the bottom of the command module.
Apollo blazes across the heavens, coming back to Earth at 25,000 miles an hour.
Parachutes deployed, and Columbia splashed down safely into the Pacific Ocean. And what was once a 3,000-ton behemoth of rocket, fuel, and freight was reduced to this: a small command module floating in the ocean, carrying 3 astronauts and rock samples collected from the surface of the moon.
That was the last video for today. Let's now talk about, as I said previously, the greatest cooperation in space exploration history. It's next slide, please. It's no, previous slide, please. It's Apollo-Soyuz. Apollo-Soyuz, yes. Everything ends sometimes. In 1975, it was an Apollo-Soyuz, the first international space mission carried out jointly by the United States and the Soviet Union. Millions of people around the world watched on television as the United States Apollo model docked with the Soviet Union Soyuz capsule. The project and its memorable handshake in space was a symbol of peace between the two superpowers. Of course, I'm sorry. It is generally considered to mark the end of the space race, which had begun in 1957 with the launch of Sputnik 1, as we already mentioned. So that was the first phase of the space race. You know that after that, there was a Star Wars program by Ronald Reagan and the US system, with the United States. There was a space shuttle. There was a special, similar to space shuttle, space ship called Buran. It was a mere orbital space station, the first orbital space station by the Soviet Union after Soyuz space station. And of course, the International Space Station, will mention something about it next. So let's go further. Let's skip nowadays. We'll talk about nowadays later. Oh no, okay, let's go to this. I'm sorry, I cannot remember about that slide. So yeah, let's talk about nowadays. You know that Elon Musk, that's a really, really common thing. So of course, as I already mentioned, the cooperation between United States and Soviet Union and Russia later, Russian Federation, finishes with International Space Station, not finishes now, of course. It was the most expensive structure in human history. It was $400 billion spent on the International Space Station. And of course, you know that International Space Station will walk on our orbit till 2024. That's a really long term, 24 years for International Space Station. That's a really great achievement by our two countries. So we also need to mention Soyuz spacecraft, the most reliable launch vehicle in the world to date. It's have about 140 flights since 1960s. You already know that Soyuz 1 and Vladimir Korolev, who died after the Soyuz 1 bad mission, was not very successful mission. But after that, Soyuz became a really, really reliable launch vehicle, and Elon Musk just cannot beat this achievement, because he simply cannot have such time from 1960s like Soyuz has. Soyuz had, I'm sorry. So let's talk about Soyuz rocket. The most reliable rocket, like, you know, we have a Soyuz spacecraft and we have a Soyuz rocket, that's okay in Soviet Union. It has over 1,700 flights since debut in 1966. And this is the most frequently and the most reliable launch vehicle in the world. It is manufactured by Progress, Joint Space Center Progress. It is located in Samara, Russia. So we are Samara University, and in our city there is a Joint Space Center progress. And this is the beginning of a space cluster here in Samara. And we in Russia, we have two joint schools in aerospace engineering. It's in Korolev, near Moscow, and here in Samara. So, and of course, we cannot mention, we can mention, of course, we need to mention SpaceX, the first successful private company, creates the first successful private working rocket. It's Falcon 9 and a spaceship called Dragon. And of course, you know, Crew Dragon or Dragon 2 has already traveled to space station and already traveled two astronauts to space station. And it was the return of the United States to the space. So they will also have, now they also have their human program in space after the ISS. So you know that United States astronauts, of course, travel to ISS in the Soyuz rocket. So let's move on. Let's go to the next slide. So now let's talk about physics. Let's talk about physics. That's a pretty interesting thing, and it's pretty easy. So you know that rocket in its simplest form, rocket in its simplest form is a chamber enclosing a gas under pressure. A small opening at one end of the chamber allows the gas to escape, and in doing so provides a thrust that propels the rocket in the opposite direction. And a good example of this is a balloon, simply a balloon. Air inside a balloon is compressed by balanced rubber walls. The air pushes back so that the inward and outward pressing forces are balanced. When the nozzle is released, air escapes through it, and the balloon is propelled in the opposite direction. So that's the basics of rocket equation. That's the basics of rocket motion. So now let's talk about basics in physics. I think you all know Newton's three laws of Newton, three Newton's laws, but let's talk about them, how they applied to rockets and rocket motion. So this law of motion, Newton's first law, is just an obvious statement of fact, but to know what it means, it is necessary to understand the terms rest, motion, and balanced force. Rest and motion can be thought as of being opposite to each other. Rest is a state of an object when it's not changing a position in relation to its surroundings. If you are sitting still in a chair, you can be said to be at rest. This term, however, is relative. Your chair may actually be one of many seats in a speeding airplane. The important thing to remember here is that you are not moving in relation to your immediate surroundings. Motion is also a relative term. All matter in the universe is moving all the time. But in the first law, motion here means changing position in relation to surroundings. A ball is at rest if it is sitting on the ground. The ball is in motion if it is rolling. A rolling ball changes its position in relation to its surroundings. In rocket flight, the forces become balanced and unbalanced all the time. A rocket on a launch pad is balanced. The surface of the pad pushes the rocket up, while the gravity tries to pull it down. As the engines are ignited, the thrust from the rocket unbalances the forces, and the rocket travels upward. Later, when the rocket runs out of fuel, it slows down, stops at the highest point of flight, then falls back to Earth. So that's the basic things of Newton's first law. You can also see text on slides. So let's go to Newton's third law. That is also pretty common thing. I think you know it from school. So for the time being, we will skip the second law and go direct to the third. This law states that every action has the equal or opposite direction. If you have ever stepped out of small boat that has not been properly tied to a pier, you will know exactly what this law means. So you can see that exhaust flow pushed backwards and engine pushed forward. So that's the Newton first law is the basics of rocket motion. It's the basics of rocket equation. So yeah, now let's move to our Newton's second law. Let's go to our Newton's second law. This law of motion is necessarily a statement of a mathematical equation. So yeah, you can see our first equations here. The three parts of the equation are mass, acceleration, and force. Using letters to symbolize each part, the equation can be written as follows. You can see F, it's mass, and acceleration. So yeah, let's apply this principle to a rocket. Replace the mass of the cannonball with the mass of the gases being injected of the rocket engine. Replace the mass of the cannon with the mass of the rocket moving in the other direction. Force is a pressure created by the controlled explosion taking place inside the rocket's engines. That pressure accelerates the gas one way and the rocket to another. So yeah, that is a pretty common thing. I think you understand what I'm saying. because Newton's second law also can be restated in the following way. The greater the mass of rocket fuel burned, and the faster the gas produced can escape the engine, the greater the thrust of the rocket. You will understand it clearly after we present you at Tsiolkovsky equation. So now let's move all of Newton's law to motion together. An unbalanced force must be exerted for a rocket to lift off from a launch pad or for a craft in space to change speed in direction. That's the first law. The amount of thrust or force produced by a rocket engine will be determined by the mass of rocket fuel that is burned and how fast the gas escapes the rocket. That's the second law. And the reaction of motion of the rocket, the motion of the rocket is equal and in the opposite direction of action of thrust from the engine. That's a third law. So yeah, that's a pretty common thing. I think you studied from your school. I think you can say yes. I think that's pretty clear for you. So yeah, now we try to explain to you some more harder principles of rocket equation. Anton Podrodnev can continue, and I will tell you something about rocket in a nutshell.
Okay, so I'm going to talk about the rocket structure. And so in the rocket, there are many parts that make up whole rocket. There are four major systems in a full-scale rocket. The structural system, the payload system, the guidance system, and the propulsion system. So let's go through them. The structural system or frame is similar to the fuselage of an airplane. The frame is made from very strong but lightweight materials like titanium or aluminum, and usually employs long stringers which run from the top to the bottom, which are connected to hoops. These parts in a rocket are called frames. Then the skin is attached to the stringers and hoops to form the basic shape of a rocket. Fins are attached to some rockets at the bottom of a rocket to provide stability during the flight. The payload system of a rocket depends on the rocket's motion. Modern rockets are being developed for launching satellites with a wide range of missions: communication system, weather monitoring, spine, planetary exploration, and observatories like Hubble Space Telescope. The guidance system in a rocket may include very sophisticated sensors, onboard computers, radars, and communication equipment to maneuver the rocket in flight. The guidance system must also provide some level of stability so the rocket during flight does not tumble. As you can see on the figure, most of full-scale rocket is a propulsion system. There are two main classes of propulsion system: liquid rocket engines and solid rocket engines. For the purpose of weight determination and flight performance, engineers often group the payload, structure, propulsion structure like nozzle, pumps, tanks, etc., and guidance into a single empty weight parameter. The remaining propellant weight then becomes the only factor that changes with time when determining rocket performance. Let's talk about multi-stage rockets. There are two types of rockets: single stage and multi-stage rockets. V2 on the figure is a single stage rocket. So the question is, what is the difference between a single stage rocket and a multi-stage rocket? First, let's define what a rocket stage is. A rocket block is each individual part of a rocket what is designed to accelerate a payload. The mass of a rocket block consists of the mass of the structure and the mass of the fuel. A rocket stage is the connection of rocket blocks with a useful payload. The payload of the first stage of the rocket is the second stage. For the second stage, the third stage, etc. Payload of the last stage of a rocket is our payload placed in a given orbit. For example, basic satellite. It's easy to understand what a single-stage rocket is: a rocket which has only one block. A multi-stage rocket is a rocket which has more than one block. Multiple-stage rockets have better range and velocity. They are much effective in injecting their satellites in different orbits at a different individual velocity. Let's meet with some basic definitions from rocket science. First is the Tsiolkovsky number Z of a single-stage rocket. So it is the ratio of the initial mass of a rocket to the mass of a rocket after fuel realization. The Tsiolkovsky number of the if stage of a multi-stage rocket is the ratio of the initial mass of the if stage of a rocket to the mass of the if stage of a rocket after the fuel realization. The variable characteristic velocity is the velocity of a rocket, which it would acquire after all the fuel was used up in a straight line in airless space and without the influence of the gravitational forces of celestial bodies. This velocity can also be called the ideal rocket velocity. This velocity can be calculated using the formula derived by Tsiolkovsky formula, and you can see it on the slide. Okay, so next. The ideal required velocity, characteristic velocity, is the velocity what must be given on the Earth's surface by an impulse to the payload for it to enter a given orbit at a given velocity without taking into account losses due to atmospheric drag. So here, capital R is the Earth radius, uppercase R is the radius of target orbit, and mu is the gravitational constant of the Earth. The next equation is the required characteristic velocity. So it is a velocity what is necessary to ensure the launch into orbit or give to the payload of a given velocity vector at a given point in outer space, taking into account all losses like aerodynamic losses and gravitational losses. So it is just the ideal required characteristic velocity plus velocity losses. Gravity and aerodynamic friction are the cause of velocity loss. Okay, taking into account the definition given above, so let's try and quickly define the mass ratio of a rocket, which should put the payload into orbit of a height of 200 kilometers high. So we need to note what velocity losses are 2.2 kilometers per second, and the effective exhaust velocity is 3,500 meters per second. Okay, so our first step is to find the ideal required velocity. So what velocity we need to give our rocket to put it into an orbit of 200 kilometers high. We can use the formula, the equation below. So, and after making simple calculations, we get about 8 kilometers per second. Okay, our next step is to find required characteristic velocity. So, okay, what velocity we should give our rocket, taking into account gravity and the aerodynamic factor. This is quite easy. We just need, we already know losses by our task. We just need to sum up the ideal required characteristic velocity, which we already got, and the velocity losses. And we get roughly 10 kilometers per second. Okay, next. In order to find the mass ratio, we have to use Tsiolkovsky formula. In this formula, we deduce the required mass ratio through the available characteristic velocity. After making simple calculations, we get the mass ratio of a rocket at launch pad to the mass of a rocket when the fuel is consumed is roughly 19. Okay, so this means what the original rocket on the launch pad is roughly 19 times heavier when all the rocket fuel is depleted. So that's a lot of fuel. Okay, the mass fraction is necessarily always smaller than 1. And in the task above is equal to 0.95. So 95% of rocket's mass is a fuel. In fact, the rocket Soyuz had a mass ratio about 7.4, what means around 86% of mass rocket is a fuel. And Saturn V rocket, for example, has a mass ratio of roughly 9. And this means what the roughly 90% of rocket of Saturn V mass is a fuel. Okay, so we finished with it, and you can ask us your questions after Roman's speech.
Yes, thank you, Anton. So anything great always starts small. Before developing, building, and launching a rocket, you need to learn a lot, perform a large number of experiments. Today, in our Student Aerospace Association Rocket Lab, just like Sergei Pavlovich Korolev, we step by step on the difficult path of space exploration. So I'm going to speak about our project TSR 2.0, which we realized at the special event Sea-Space in 2018. TSR 2.0 is a two-stage rocket project with an active second stage. It is two blocks with their own onboard electronics and telemetry systems, recovery system with parachutes, and searching system after rocket landing. The main experiment of project was stage separation and activation of second stage engine in the flight. To provide it, we developed a stage separation system and ignition system of second stage. The separation system located on the first stage is a 3 servers with screws, own microcontroller, and few sensors to detect separation. Before flight, the servers tighten the screws into the threaded holes on the lower frame of the second stage. So both stages are connected, forming a threaded joint. At separation time, the server starts unscrew threaded joint, and the spring pushers help to move stage from each other. Ignition system. The ignition system defines automatically the optimal time to activate the engine of second stage. It located on the second stage and contains in the important model of orientation. Using gyroscope, the orientation model defines the angle position of the rocket, avoiding the engine activate when rocket orientation wrong. These are the azimuth angle omega and the inclination angle phi. Telemetry. The additional experiment was collecting flight data to create the mass model of rocket flight using experimental data. Telemetry system measures pressure, line speed, angular speed, and movement. Pressure is measured by a barometer, line and angular speed by accelerometer and gyro. Movement are measured by GPS. The main goal was to develop the two-stage rocket product and its systems. The main thing was during this work gave the opportunity to students gain practice and skills, and the student can use their university knowledge in realization engineering project. Why the two-stage rocket project? In 2015, a previous team developed the rocket project consists two parts, which separate in the flight, but it was not multi-stage rocket. The main reasons they motivated us to realize the TSR product were desire to use this project and upgrade it to multi-stage rocket project and use this opportunity to develop our student association. We created the project team of 12 students from different faculties and years of study. This project team is divided to two engineering teams. The electronic team was designing and manufacturing onboard electronic system. The mechanical team was developing and manufacturing mechanical system and construction of the rocket. Both teams worked independently, but often met to discuss proposals and to get feedback. So just a few photos how it was. Next. At Sea-Space 2018, we presented the launch team of 3 members, 2 mechanics and 1 electronic engineer. The first launch with the dummy second engine was successful. Separation system has worked properly and stages were separated. Ignition system activated the igniter of second engine at optimal time. Both stages landed soft by parachutes and were recovered by team. All system worked nominally. But the second launch with real engine of second stage we could not provide. Because problems with the orientation system, the measurement error of angles increased fast. The team could not quickly fix it and provide the second launch in the time. So, total statistics of recovered flight data in the slide. In conclusion, if you are interested in a such type of project or you want to make a project together, just write an email and send it on our email address. We are open for international cooperative projects. Thank you for your attention.
Yeah. Anything from you?
Okay, so guys, you can ask us any questions for you want. You can ask us through chat or through video chat.
So yeah.
Hello.
Let's talk something. Yes, let's end this whole lesson. So you can send something to my. Can you open the demonstration again? Because there are some interesting things. So you can, of course, you can send an email to my email. It's here, juperdonov@outlook.com. Or you can also go to our social medias. I think it will be only Instagram for you because, you know, VK, it's contact in Russian. That's a pretty Russian social network. And I don't think you have an account with VK. So if you can turn on all of your cameras, all of members who can hear us, it will be very great because we cannot understand how many of you is still here and is it successful? Is our lecture successful or not? If you have any questions, you can ask them right now. We have maybe about 10 or 50 minutes. And you also in a chat or just turn on your mic and just say it. And we will answer you, or just contact us via email or just go to our direct in Instagram. So yeah, we'll wait your questions and after that we'll finish our lesson for today. Yeah.
Yep.
Hello. Can you hear my microphone?
Yeah, we can hear you.
I just want to ask, it is not about the mathematics and also the physics, but about the history that previously that you explained just now.
Can you repeat the question? We'll get our volume a little more because we can. Yeah, Kiki, say it again, please.
Okay. So I want to ask regarding the history. Previously you explained, not the physics and the mathematics that ones that you explained just before. So in particularly nowadays, that was in the Soviet days, Soviet Union days. So like now we can see in US now, they have SpaceX that are pioneering their engineering in rockets. So how about Russia?
So your questions about private companies in Russia, and I understand it correctly? How about Russian space right now?
Yeah. How about Russia space right now?
In Russia, we simply haven't enough and cool big private companies. But what about Russia in space now? So yeah, Russia had tough times in space now because we simply cannot have a lot of funding just like NASA or just like SpaceX, and you know that a lot of developments that has Roscosmos. Roscosmos is a federal space agency in Russia. A lot of technical things. We have it from Soviet Union. It's a Soyuz spacecraft. It's Soyuz rocket. It's the International Space Station, of course. It was built during the Russian Federation, of course, but it has a lot of technologies from Soviet Union. So now Russia develops a lot of things. We develop our super heavy missile called Angara, super heavy rocket, Angara A5, Angara 5 in Russian. We also develop but we developed it already 12 to 20 years, but
More than 20
more than
years.
20 years. So that's not a very successful project. And we have only 2 flights of Hungary 5. So yeah. And Roscosmos also develops a new spaceship called Oriole or Eagle in English. It's just like Dragon, Crew Dragon. It also can carry 6 cosmonauts, not astronauts. Cosmonauts, it's astronauts in Russian. So yeah, and now Russia tries to connect with NASA in a project called Deep Space Gateway. I think you know something about it. It's an orbital station near the moon. And now a lot of countries already partnered with NASA in this Deep Space Gateway, but Roscosmos simply refused to partner with NASA in that level, like European Space Agency, like Japanese Space Agency, because Roscosmos thinks that we have a really big infrastructure, we have a really big history of space exploration. And Roscosmos thinks that he's not number 1 maybe space agency in the world, but it's number 2, and that is debatable. So yeah, so now rocket, now space engineering in Russia is not very popular thing, and that's a really sad thing to understand.
Yeah, I understand that.
Yeah, so now Russia is not very good in space exploration. All we have right now, it's just updated things from Soviet Union. So yeah, so that's sad thing, but that's true. That's pretty patriotic thing from us. We say it too clearly. So if you have any questions about history, about mathematics, about Tsiolkovsky's equation, because I need to sorry that we have some little Russian accent, I think little. So yeah, you can see.
Riveta, can I do a small question? Is it possible for you to send this presentation to our emails, or I don't know, via WhatsApp or something like that?
Yeah, you can please just contact me, because I don't know your emails right now. You can just contact me via my Outlook.com, and I will send you this presentation. I will send you links to videos on YouTube, because we're all on YouTube. And I can also send you our text, so you can understand what we are saying, because I think it's hard.
Отлично. Спасибо.
So, if you have any questions, do you have any questions for me?
May I?
Yeah, hello.
So I have 2 questions. The first one is about how are the opportunities in working in this area in Russia? Are all they linked to a governmental company or something so, or what are the opportunities around there?
Your question is about opportunities of working in the space industry in Russia. Yeah, I understand.
Yeah.
Okay, so in Russia we don't have many private companies like in America. SpaceX, we have Blue Origin, they have a lot of Firefly Aerospace. So yeah, in Russia we simply there are not so many private companies, and the main thing where you can work when you try to go to aerospace engineering, it's a Roscosmos, so Federal Space Agency. But there's not very it's not very prestigious maybe to work on Roscosmos, because they don't have enough salary for maybe 60 or 70% of students. They have a lot of secret things, and we just work for them, and we cannot go abroad because that's a problem. We have a lot of secrets on Roscosmos, and of course the maybe 80%, 70% of Roscosmos engineering stuff is military stuff. And if you are a pacifist and you think that you cannot do something that can kill human or something, that's a problem to working on Roscosmos. So yeah, basically we have only one opportunity here. We have Roscosmos, and a lot of we also have a lot of factories who works for Roscosmos, but they also very closed. They also not very rich. So yeah, so the main thing in Russia is Roscosmos. Yeah, the main buyer of all of developments from that factories is Roscosmos. So yeah.
And in Samara University, do you have some research for Roscosmos or something so?
Yeah, that's a pretty interesting thing, because we simply don't have enough places to work. for us. But we have a lot of researchers in Samara University. We have a lot of researchers in in other universities in Russia, in Moscow. So yeah, for example, my department develops a nanosatellite. It will be launched in 2021 into orbit. It will be first satellite which will be launched by my department. So yeah, we have a lot of researchers here about space in different directions. So we research nanosatellites, we research rockets, we research spacecrafts, but Roscosmos trying to funding all of that. But that's a problem for him because it's not very rich agency. For example, to compete with NASA. So yeah, we have a lot of research.
And the project of yours, how is it founded? Where does the money come from?
It is funding from university. So university gave us some money. Is correct? University funders. So yeah, university mainly the biggest money that we take it was from university. Of course, university funding us. Of course, we have a lot of funding moments, but we are not very rich, as I said previously. So, for example, we cannot simply go to our, United States have really strong competitions in rocket engineering, in rocket development, in student rocket development. But we cannot really go to United States because it's a little expensive for us. So we need to go 6 people to United States, and this is really expensive to go to United States and again. So yeah, but we're trying to do something. In Russia, we also have biggest competition. It's called Roskonsat. It's biggest competition in Russia, and there's also some international students participating in that competition, and we also compete with our guys in there, not only in Space 2020.
Perhaps the last question, do you have any software for calculations, for simulation about the velocity and something so?
Yes. Do we have any programs or any
software?
In software, yeah. We we have.
So we built like mathematical models for rocket, so we can calculate dynamics of rocket, aerodynamics. So and for example, we use for that MATLAB program to make simple program Python, and for aerodynamics calculations and
some structural
we use FEMAP, SolidWorks, so something these type of programs. You may know this program.
Sure. Thank you.
No problem. Okay, guys, if you don't have any questions, I think we finish.
Please email us. We will send you a presentation. You can also ask questions via email. So we will be really pleased to answer you. So yeah, maybe that's all. So thank you for your attention.
Okay, thank you guys for your attention.
You are the greatest viewers that we ever had. So yeah, let's go. So thank you very much. Let's close our Zoom. Let's see you. Please answer ours.
Okay, see you guys.
Thank you. See you.
Can we take picture first?
What do you see?
Can we take group picture first?
Yeah, we can take a group. Yeah, we can take a picture.
You can turn off your slide here.
Oh yeah, we can take a picture. So now we will stop our demonstration of my screen. Yes. Yeah. So yeah. So now while making it. Yeah, we're ready.
Smile.
Yeah. That's we already. So our technical advisors helps us. They are under this wall, behind this wall. I'm sorry, not under. So yeah, that's all. Thank you for your attention again. So let's stop our translation. So bye bye.
Bye guys.
Bye.
Thank you.